Next, we will learn to design BCD adder. First of all, we need to know what is BCD adder. If we have a number 3 and we want to add this 3 with 4, so both are in decimal. If we convert this decimal to BCD, so 3 is represented by 0, 0, 1, 1 and 4 is represented by 0, 1, 0, 0. This is not binary, this is BCD. After adding these two numbers, 1 plus 0 will give us 1, 1 plus 0 will give us 1, 1 plus 0 will give us 1, 0 plus 0 will give us 0. And the corresponding decimal number can be written as 7. Well, here we can use 4-bit binary adder in order to get this result. But the problem will occur if the addition, that means summation, becomes more than 9. For example, in your previous lectures, we have seen that if we want to add 6, which is in decimal, plus 5, which is also in decimal, what will be the result? 6 can be represented by 0, 1, 1, 0, and 5 can be represented by 0, 1, 0, 1. If we add these two numbers, the result will be 1, 1 plus 0, 1, 1 plus 1 will give us 0, and carry 1 will come here. So this number is not BCD. Here we are getting invalid BCD. If we get invalid BCD, in order to get the correct result, what we need to do? We need to add 6. We know the process. After adding 6, what will be the result? If I write the result here, we'll get 1 plus 0, 1, 1 plus 1, 0, then carry 1 plus 1 will give us 0, then carry 1 plus 1 will give us 0, and finally 1. So here we have this one set of BCD, and this is another set of BCD where we can put 3 zeros at the beginning. This number is the representation of decimal 1, and this number is representation of decimal 1, so we'll get the result 11. Here we need to design a BCD adder where we'll provide BCD input and the outputs, that means the added value of these BCD numbers, will be shown in BCD as well. So in the output side we'll get BCD output, not the binary addition. Let's see the designing procedure. We already designed 4-bit binary adder in our previous lectures. In 4-bit binary adder, we have 4 inputs: A0, A1, A2, A3, B0, B1, B2, B3. A0, A1, A2, A3, B0, B1, B2, B3. We have carry in here, C in, and carry out, C out, and the binary summation output S0, S1, S2, S3, and C out. This is 4-bit binary adder. Remember, whatever binary input we'll give, we'll get the binary summation. For this adder, we will not get BCD summation. And what we have inside this box, we already designed that we have 4 full adder circuit, and we know the configuration of each full adder circuit. So the circuit diagram inside this box is known to us from our previous lectures. Now let us see how can we make a BCD adder by using 4-bit binary adders. Here we can control the inputs. Inputs will be BCD. A0, A1, A2, A3 inputs will be BCD. Also B0, B1, B2, B3. These inputs will also be BCD. These are from the user sides. So whenever we are saying that the inputs are BCD, that means A0, A1, A2, A3 can have a maximum value of 1001, and B0, B1, B2, B3 that can have maximum value of 1001, that means 9. Now this 4-bit binary adder is okay if the summation value is less than or equals to 9. That means if we add 3 plus 2, we'll get 5. And 5 in binary and 5 in BCD both are same. That is why it will not create any problem. But the problem will occur when the binary addition, this binary 4-bit binary adder will give us a result binary summation which is greater than 9. For example, 10 or 11. For 10, the binary output is 1010, but for 10 the BCD output should be here 0000 and 1 carry out. So how can we do that? For this purpose we are going to use another 4-bit binary adder. Let us take this binary adder, take a copy of this. Why am I taking copy? I'll let you know. Let's remove these portions, names as well. So this is 4-bit binary adder number 1, this is 4-bit binary adder number 2. Suppose we are giving two BCD numbers here. Now after adding these two numbers, if the number is less than or equals to 9, we do not have to add anything with this number. But if the number is greater than 9, we need to add 6 with this result in order to get the correct BCD. So let's take this output as one of the input of the second adder. Here they are connected. Next, we will add 6 or 0 with this number. If the intermediate result that we are getting from the first 4-bit binary adder, let's name this output as Z0, Z1, Z2, Z3. If this summation is less than or equals to 9, then we do not have to add anything here. If this number is greater than 9, we need to add 6 in order to get the correct BCD addition. We came to know about this from our previous theories. So what we are going to do, we'll design a checkered circuit. This is a checkered circuit. Let's name it by CH. This checkered circuit will take input from this, from Z3, from Z2, from Z1, and from Z0. These are the inputs to this checkered circuit. It will always check the number Z0, Z1, Z2, Z3 whether this number is greater than 9 or not, and it will provide one single output. The single output, this is the output, will be connected with these two, and these two inputs are grounded. That means we are giving 0 here and 0 here. Why? In order to make it 6, we need to give 0, 1, 1, 0, which is the binary value of 6 or BCD value of 6. So we can see either we need to add 6 or we need to add 0. For both the cases, the least significant bit and the most significant bit are 0. That's why we are making them forcibly 0 by connecting with the ground. Now, after examining these values, if the checker finds that this Z0, Z1, Z2, Z3 is greater than 9, it will give us output, checker output CH equals to 1. When it will give us 1, this 1 is connected with these two inputs. So eventually in the second input of this binary adder will get 0, 1, 1, 0, which means 6. So if Z0, Z1, Z2, Z3, this value is greater than 9, then automatically 6 will be added with this number and we'll get the corresponding BCD value. But if this number is less than or equals to 9, then the checkered circuit output, CH output will be 0. Eventually it will be 0, 0, 0, 0. So 0 will be added with this output, so nothing will happen. This output will come directly here, which is the BCD addition. So finally we'll get the BCD output here. We'll get BCD output. Now let's start designing this checkered circuit. We can see the checker inputs are Z0, Z1, Z2, Z3 and this C1 carry output of the first 4-bit binary adder, and the output of the checker circuit is CH, which has only one single output. Now before I proceed, what can be the maximum number here? what is the expected maximum number of Z0, Z1, Z2, Z3, C1. As we are saying that the inputs are BCD, so the maximum value here will be 9 and maximum value here will be 9. That means the maximum value that will be appearing both in A and B will be 9 plus 9, and we may have one carry from the previous addition, so the maximum value in the first binary adder, 4-bit binary adder, will get 9 plus 9 in decimal and one carry from the previous addition, so which is equals to 0 0 0 1, here 1 0 0 1 1 0 0 1. After adding these numbers we'll get 1 1 0 1 plus 1 0 and 1 carry. So this is the maximum output we'll get as Z0, Z1, Z2, Z3 and C1. So in the 4-bit binary adder, the output will start from 0 0 0 0 0 and it can go up to 1 0 0 1 1 if the inputs are strictly maintained as BCD. So let us start designing the checker circuit. Here we need to design this checker circuit. We have Z0, Z1, Z2, Z3 and C1 as input that are coming from the first 4-bit binary adder and one single output. This output will be 0 if this number is less than or equals to 9. This CH output will be 1 if this number is greater than 9. So let us start plotting the truth table for this checker circuit. The inputs are binary sum of binary adder number 1. Here we are writing Z0, Z1, Z2, Z3 and finally C1. In the output side we have CH. Let me write the decimal number, corresponding decimal number as well for your better understanding. If the number that will be appearing here is 0 0 0 0 0, then the checker output should be equals to 0. The decimal value of this input is 0. Now next 0 0 0 0 1, checker output should be 0 because 1 is less than 9. For 2 0 0 0 1 0, 0. Now when we have binary sum up to 9, the checker output will be 0 because we need to add 0 with our previous addition. Now if this value is greater than 9, we need to add 6. In order to add 6, we need to have checker output equals to 1. So for the next number, next binary number 0 1 0 1 0, the checker output should be 1 from here. 11 Let us write the remaining values here. For 18, the inputs are, the output will be 1. For 19, we may have other combinations. Using 5-bit case, we can go up to 31. However, from 20 to 31, all these numbers are don't care conditions. Why? Because we know these numbers will never appear. The maximum value we can get here is 9 plus 9, that means 18 plus 1 from the previous carry, that is 19. So the maximum value we can get here is 19. That is why the remaining values will be considered as don't care condition. Now let us plot the Carnot map for 5 variable case. I'm showing you the simpler method for dealing with 5 variable kernel maps. Here the most significant bit is C1. So we'll keep C1 aside. Remaining 4 bits will be taken as we take for our conventional 4-bit kernel map case. There will be 2 kernel maps for Z0, Z1, Z2, Z3, considering C1 equals to 0 first and then C1 equals to 1. Actually, as we have 5 variables here, so using 5 variables we can have 32 combinations. So we need 32 smaller cells. So in this box we have 16 smaller cells, and in this box we have 16 smaller cells, and total we have 32. Now this box will be considered for C1 equals to 0, and this box will be considered for C1 equals to 1. Now most significant bit will be written here: Z3, Z2, Z1, Z0, Z3, Z2, Z1, Z0. So if we have a value C1 equals to 0, 0, 0, 0, 0, 0, then C1 equals to 0, 0, 0, 0, 0, this box will represent that value. Again, for 1, 0, 0, 0, 0, we have C1 equals to 1, C1 equals to 1, and other Z3, Z2, Z1, Z0s are 0. So C1 equals to 1, 0, 0, 0, 0 will represent the corresponding value of this. So if I say in decimal numbers, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. So starting from 0 up to 31, we have total 32 number of cells. Now for this CH output, let's start putting the ones. We'll get 1 at 10th position, 10 decimal position. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here it will be 1, 11, 12, 13, 14, 15, 16, 17, 18, 19. We have ones up to 19, and 20, 21, and remaining boxes can be taken as don't care conditions after 19. So I'm placing don't care conditions here. Now while mapping, you'll consider these boxes are on the top of each other. Remember, if they are on the top of each other, then the smaller rectangles are aligned from top to bottom. They can be considered as adjacent cell. Let us start taking the rectangles, then it will be clear to all of us. First of all, what is the biggest box can we take? We can take the complete box here. Here this red box is true for all the combinations of Z0, Z1, Z2, Z3. So we can ignore Z0, Z1, Z2, Z3. But C1 has value equals to 1. So this red box is true for C1 equals to 1, but not for C1 equals to 0. So we cannot ignore C1. So the name of this red box is C1. Now what is the next box? We can take this 4. After taking this, you'll consider this map is placed on the top of this map. So if we place it on the top of this, can we take the adjacent cells containing these 4 ones with the bottom one? Yes. You see, this one is having cross at the bottom. At the top one, we have cross at the bottom. What we can say, this green box and this green box, they are also adjacent. So these 2 green box will be considered as one box. Now name of this green box. The name of this green box is, this is true for Z3, Z2. Z3 equals to 1, Z2 equals to 1. So we'll write Z3, Z2. And this is true for all the combinations for Z0, Z1. So we are ignoring Z0, Z1. Now this is also true for C1 equals to 0 and C1 equals to 1. So we are ignoring C1. So the name of this box will be Z2, Z3. Let us deal with this remaining 2. We can take 4 boxes. Now once we finished taking these 4 boxes. Now let's consider they are on the top of this second Carnot map. Now can we say that we have an adjacent cell in the top and bottom box? Yes, we have don't care conditions at the same positions of this blue box. So we can say from the top to bottom, these 2 boxes are one single box. Now if we name this blue box, this is true for Z3 equals to 1. So we'll write Z3. Z2 equals to 1, Z2 equals to 0, so ignore Z2. Z1 equals to 1, Z1 equals to 1, write Z1. Z0 equals to 1, Z0 equals to 0, so ignore Z0. These 2 blue box is true for C1 equals to 0 and C1 equals to 1, so ignore C1. Finally, the CH function can be written as C1 plus Z3 Z1 plus Z3 Z2. This mapping was done for CH output. Now if we draw the circuit diagram of this checker circuit, we have Z0, Z1, Z2, Z3 and C1. We need to AND Z3 and Z1. The output will be passed through OR gate. We have Z2, Z3 ANDed and C1. All these will pass through OR gate and will get CH output, checker output. Finally, if we implement the checker circuit here, we have C1 Z3 into Z1, so Z3 and Z1, they will be ANDed. Z3 Z2, we have Z3 Z2, they will be ANDed. The output will pass through OR gate and this C1 will also pass through OR gate, and this checker output will be connected with this. Now this circuit will act as BCD adder. Whenever we are giving BCD inputs, if the output is less than or equals to 9, then 0 0 0 0 will be added with this number, so this number will appear directly here. But if Z0, Z1, Z2, Z3, C1 is having a value greater than 9, then this circuit will make the output to be added with 6 and will get the corresponding BCD output. So this is the BCD adder circuit. Inside this box we have this circuit, and inside 4-bit binary adder we have 4 full adders. This carry input will be used for adding carry from the previous addition, and this carry in can be made grounded. I hope the circuit diagram is clear to all of you.